안녕하세요 여러분, 해리입니다. So in the previous videos we have talked about the basic differentiation methods, so all these formulas, chain rule, product rule, and quotient rule. And we've also seen some basic applications, so max and minimum, and finding maximum and minimum using the first derivative test. And this test we can also look for the increasing and decreasing region of the original function. And we can also use second derivative test to justify a maximum or minimum point. And also using the second derivative test, we can find the concavity of a function. And we've also learned how to find the tangent and a normal line of a curve at a certain point. And we've done some basic kinematics and rate of change. So for today's video, if you're in Math SL, IB Math SL, or IGCSE students, you don't have to watch it anymore. Today, we're going to do, this video is for HO students only, and for HO students, we are going to learn some more formulas that you have to know. So first, we start with further trigonometric formula, trig functions, derivative. So remember, derivative means differentiate function, okay? So in HO, you learn three more, right? Secant, cosecant, and cotangent. So first, secant is a reciprocal of cosine, right? So that means if we differentiate secant x, then simple. So we are basically trying to differentiate 1 over cosine x. So you can make this as to the power of -1, and you can apply chain rule, and you'll have secant x tan x. If you directly differentiate this, you will not have in the form of this. So I'll just try for you. So we use chain rule, right? And so what we substitute cosine, so that we make in a form of x to n. And if it's in the form of x to n, it's very simple, right? So we substitute the function first, and since we have to differentiate by x, we differentiate this u by x, but the variables are not synchronized, so we multiply 1, and that yields this. And du over dx, okay, u is cosine x, that means du over dx is just differentiating cosine x by x, so negative sine x. So we have negative sine x. So this negative sign, two negative signs cancel, so it becomes positive. And it's u to -2. U to -2, but u is cosine. So this is what we get, and how do we make this into that? So we have two cosines, right? So we have two cosines multiplied in the denominator, and we have one sine. So if we make this into tangent, then we have 1 over cosine x, and that's secant. So that's how we get it. And the second thing is cosecant x. So cosecant x is 1 over sine x. And again, if you want to know how we can find the derivative of cosecant x, you can use the same idea. So it's simple. So if a function is cosecant x, and if you differentiate it, you'll have negative cosecant x times cotangent x. And cotangent x is 1 over tan x, right? Which is cosine x over sine x. And you can use quotient rule to solve this. So if you differentiate cotangent x, you'll have negative cosecant x squared. So these are the basic further trigonometric formulas that you have to do. And now I would say the most difficult part in HO differentiation. So implicit differentiation. So far we've only seen the explicit functions. What I mean by explicit is that we could write y in terms of x. So just y equals to something. That's why we could directly differentiate it. But for example, if we have something like this, so y cubed and y squared, and there is no way you can you can rearrange this equation into y equals in terms of x. So if you are asked to find dy over dx from this function, then what do you have to do? So before we directly compute it, so I'll just quickly write something. So yeah, implicit functions, so you'll have a function in terms of y as well. Then how do we differentiate this by x? Is that we apply chain rule. So what does this mean? The function is in terms of y. That means in order to differentiate this, we have to differentiate it with y, right? dy. And in order to compensate for this change, we multiply dy so that it cancels out. So basically, I have multiplied 1. And we keep this dx here. So that will give us f prime y, and that's dy over dx. So now if we rearrange this, then we can possibly find dy over dx. But just by looking at this formula, it's not really convincing. So I will tell you how to do it using this example. So this is a function that we have. And note that we have two variables, x and y. And you have to differentiate the entire both sides by dx. By x. So let's try to differentiate it. Okay, so there are multiple terms, so we can just differentiate term by term, right? X squared. So if you differentiate x squared by x, we'll have 2x. Simple. Now the problem is x times y cubed. Again, I tell you again. So these two are variables. So just consider y as like a function of f. That means we can apply product rule. So we differentiate the first one, x, then it will yield 1, right? So 1 times leave the function, and then we leave the first function and we differentiate y cubed. But what do we differentiate with? X, right? So we can't differentiate it directly because we don't know what y is. So we leave it like this. So that means we have to differentiate y cubed by x. And similarly, we have y squared. So we have to differentiate y squared by x. So, and again, we don't know what y is, so let's leave it like this. And differentiating 1 by x is 0. Differentiating a constant, right? It's 0. So we have this, and note that, so this is in y, but we have to differentiate by x. So what do? We use chain rule. Right? And again, same thing for this. We use chain rule. Then, if we switch the order, since the order in multiplication doesn't matter, so we can write this as dy cubed over dy times dy over dx. And dy cubed over dy, that means we're differentiating y cubed by y. So we have 3y squared. And we leave dy over dx because we can't do anything further. And same thing for this. So similarly, we switch the order, then y squared, we differentiate by y. So 2y and we have dy over dx, and that will equal to 0. And what do we have to find? We have to find dy over dx, and we see that dy over dx are here, these two terms. So why don't we factorize this by dy over dx? So we have 3xy squared from this, and plus 2y. And we don't need these terms, right? So why don't we just move it to the right hand side? So we have this. Therefore, dy over dx will equal to this. So the important thing for implicit differentiation is that, so you'll have two variables. So this y is basically like a function. So it should be a function of x, but just the fact that we don't know yet. We don't know. So what we can do is that we just leave y as like a function of x. So we treat it as a function of x again. And we apply the same thing like product rule or quotient rule. And since we can't differentiate y by x directly, we use chain rule to make it to dy over dx. And once we have the equation in dy over dx, then factorize that out and leave the unnecessary terms away, and then write this as something, dy over dx equals to something. So that's how implicit differentiation works. And using implicit differentiation, now you'll learn some additional formulas in, for example, log, exponential, and some other trigonometric functions like the inverse. So I'll call it as advanced. It's not really advanced, but advanced differentiation rules, formulas. So first, y equals a to x, where a is a positive number, and it doesn't necessarily be e. So it can be e, the natural constant, but doesn't necessarily. So a can be anything as long as it's positive. Now, how do we find the derivative of this? So we know how to find the derivative of e to x, right? So in fact, you don't really have to use implicit differentiation for this, to be honest, because if you recall what you have done in exponential, if you have a base of a, then you can change this base to whatever you want by making it as this. And I'm pretty sure if you're in HO, you remember this. Then once you have this, y is a function of e to something, right? Then you can use chain rule, right? Or if you know it already, then you can directly differentiate it. So you put this constant out, and then you leave the constant. I leave the same thing. But that was a to x, right? So it's a to x times ln a. So yeah, you don't really have to use implicit differentiation, but if you want to use implicit differentiation, this is how you do it. So y equals a to x. So you take ln both sides. So ln y equals to ln a to x. And by the logarithm properties, we can take the power out as a coefficient. We have this, right? And now we differentiate both sides by x, because we are finding dy over dx, right? So ln y is differentiated by x, and same thing. Ln a is just a constant. So ln a entire thing is just a coefficient of x. So that one will just yield ln a, right? And this, so it's a function of y, but we're differentiating by x. So what do? We use chain rule, like what we did in implicit function. So we have dy over dx now. And what is this? We differentiate ln y by y, that's 1 over y. Right? Then dy over dx will be y times ln a, but what's y? A to x. So a to x times ln a, that's how we get it. Yeah, so it does, you can use, if you are fine with exponential or log properties, then you don't really have to use implicit functions differentiation to do it. But yeah, as long, but for example, something like this x to x is the case where you have to use implicit differentiation. So because even if you change this as base e, that means it's log base xx, and it's very difficult to solve this, right? So even if you use chain rule, it's very difficult. So what we can do for this function is that same, take ln on both sides. So ln y equals to ln x to x. And this is a power, so let's take the power out. And now we have a cleaned product of functions. And simply we can use product rule to do this, right? So it's not in exponential form anymore. So doing the same job as what we've done, so that we're differentiating this equation by x. So we use product rule, so we leave x, that's ln x, and we leave x, ln x differentiated is 1 over x. And that one, same thing, using chain rule, we have 1 over y dy over dx, and that one is just ln x plus 1. So dy over dx will equal to ln x plus 1 times y, and y is x to x. So that's how we differentiate something like this. So if a function is, let's say, like if you can't really do anything, what I mean by if you can't do anything is that if you can't apply what you have learned so far, then I would recommend you to rearrange the function a bit. So you can make it as in terms of y, I mean a function in terms of y, and apply implicit differentiation. Then for the most of the times you can differentiate the function. Right, so that was the first case, and a very similar one. So what if the base is not e? So natural log x, that's 1 over x, right? But what if the base is a? Then again, you can try to use implicit differentiation, but if you know about if you can apply log properties, then that's also fine. You don't have to use implicit differentiation. So using the log property, note that if we don't like the base, if we don't like the original base, then we can change the base into what we want, like this, right? So if you have log base AB, then we can always make a new base like that. So when C equals to B, then that's 1 over log BA. So that's why we had this formula for log, right? So that's what I used. I used the new base as E. Then what do we have? We have ln x over ln a, and ln a is a constant. Okay? Then dy over dx is simply 1 over ln a times 1 over x, because this is a constant, so we just leave it. If we differentiate ln x, we have 1 over x. So this is how we can find the derivative of log base ax without using an implicit differentiation. But if we have to use implicit differentiation, let's say, then again simple. So you rearrange this a bit, and the only way you can rearrange this is that you make the left hand side as an exponential form by removing this log away. So we make it to a to y equals to x, and a to y equals to x, again we differentiate both sides by x, so d over dx. And what's a to y? I mean, yeah, so first, okay, I'll go a bit slowly. So we use chain rule because it's in terms of y, but we have to differentiate by x. And the right hand side is just 1, dx over dx, right? So we're differentiating a to y by y. And what's this? We already have a result, right? We have this. So when a function is a to x, then it's a to x times ln a. Then if it's a to y, then simply it's a to y times ln a. equals to 1. Alright, then a2y equals to 1 over ln, oh sorry, and we have dy over dx, sorry. So let's move the entire thing away like that. 1 over a to y. But what's y? Y is log base ax. So 1 over ln a times 1 over a to log base ax. So remember, when the base of an exponential and when the base of the log on the power are the same, then that's just simply x. So that's how we could do it. Okay, so these are the two, well, I called it as advanced, but to be honest, these are still the most basic differentiation method. So yeah, that's it for log. And now, alright, so now we're going to do the last three formulas. So inverse trig functions derivative. So we have seen the three reciprocal trigonometric functions, and now we are going to look for the three inverse trig functions. So arcsine, arccosine, and arctangent. So first, y equals to arcsine x. Alright, so for this one, we have to use implicit function. That's probably the easiest. So what we can do is that we have no idea how to differentiate arcsine, right? So what we can try, so when we have to find dy over dx, we can't directly differentiate this by x because we don't know how to differentiate arcsine. So we make this into a familiar form. What familiar form? So sine y equals to x. Clearly sine is much better than arcsine. So if we differentiate both sides by x, then we have this. So again, the variables are not synchronized. Whenever you see the variables are not synchronized, then we go for the chain rule, right? So d sine y over dy times dy over dx. That's 1. So what's sine y differentiated? The derivative of sine y, cosine y, right? So that's cosine y, and if we move it, then we have 1 over cosine y, right? But what's y? Y is arcsine x, right? But seems like I have overcomplicated the case, but no, this is the correct way. So if we want to cancel out this arcsine, what we can try is to change this cosine in terms of sine, because using the inverse property, if we have a function and if we have an inverse function inside, then we remember the functions can be cancelled, so it just leaves x. Same thing, so if we have an inverse and if we have a function original function inside, then also it yields x only. So that means if we have sine and arcsine inside, then that will just yield x. Or if it's x squared, then it will yield x squared. And similarly, arcsine and we have sine x, then we'll have x. So using that idea, we can change cosine into sine. How? So recall this formula: sine squared plus cosine squared equals to 1. Then cosine squared equals to 1 minus sine squared. So cosine x will equal to plus and minus 1 minus sine squared. But for this case, we're going to stick with plus. Okay? So roots 1 minus sine squared x. But what's x? So x here is the angle of cosine. So here, the angle of cosine is arcsine. So we have arcsine here. Then this is squared, but this is arcsine. So some may think that we can't apply this because they're not the same function, but no, they are. What I mean by same function is that they're not the inverse function. So this is sine squared, this is arcsine. So some may think that they're not the inverse to each other, but sine squared basically means sine of arc sine, entire thing squared, right? And what's this? X. Then we have squared outside, so that's x squared. So it yields root, and 1 over root 1 minus x squared. This is how we can differentiate y equals to arc sine. Then 2, y equals to arc cosine. Alright, so the proof for, finding the derivative of this is also very simple because I've done it for you. So I'll just write down the results directly. You'll have this, okay? But arctan, I'll go over with you. So again, we have no idea how to find the derivative of arctan, right? So let's rearrange the equation a bit, and then differentiate it. So we differentiate x by x, that's 1, right? So again, variables are not synchronized. We use chain rule to synchronize the base by multiplying 1, and then that multiplied 1 is simply dy over dy. So d tan y over dy means we differentiate tangent y in terms of y. So since the variables are synchronized, we can directly apply the formula that we know. So if we differentiate tangent, we have secant squared. So secant squared y times dy over dx equals to 1. That means dy over dx equals to 1 over secant squared y. Okay, some students may directly write it as cosine squared y, but I recommend you to leave it as secant because I'll tell you why. So 1 over secant squared y, that means 1 over secant squared arc tan x. So it's very similar to the previous derivation. So we have secant and we have arctan. So is there any way we can make it into a composite function? The composite form of composite form of the original function and the inverse. And there is. How? So if you know some further trigonometric identities, we know that tan squared plus 1 equals to secant. And similarly, cotangent squared plus 1 equals to cosecant. And the derivation is very simple. Tangent is sine over cosine, so tan squared, sine squared over cosine squared, and then make it into common denominator. Then the numerator will become sine squared plus cosine squared, which is 1. The denominator is cosine squared, so 1 over cosine squared is secant squared. And so the same for cotangent squared plus 1. So secant squared, so secant squared is tan squared plus 1. Then why don't we write this as tan arc tan x squared plus 1, right? So secant squared x is tan squared x plus 1. So that one just becomes arc tan x. So tan arc tan x squared plus 1. And what is this? Again, this is simply x, right? Original function and the inverse. So composition will be just the input. So 1 over x squared plus 1. That's how we do it. So you can see that the derivatives of arc sine, arc cosine, and arc tangent are very, simple. So you have like a rational function and irrational, while you had trigonometric functions. So in differentiation, you'll not be asked to do this often, but these will be used a lot in integration. So don't just memorize this in one way, okay? So don't memorize so if we differentiate arc sine, we have 1 over root 1 minus x squared. Don't memorize like this. If you want to memorize it, memorize both ways, because integration you'll use these a lot. Okay? Right, so these are the 3 derivatives of the inverse trigonometric functions. And now we're actually done because we've already seen through all the application, but I'll try some applications that we've done with implicit. So what I mean is that, for example, maximum and minimum, they're very rare to, I mean, you can't really have a question with maximum and minimum and implicit, but something like tangent. So something like tangent, finding a tangent or normal line of an implicit function, and also something like rate of change, where there are multiple variables involved. But yeah, they're very simple. Just do whatever, just follow whatever you want, okay? So I've already prepared a question for you. Okay, I'm really sorry. Before we directly move to application, let's try some examples of this so-called advanced differentiation formulas, okay? So, yeah, because I've already prepared some questions, I forgot it. So, let's say we have y equals a to sine x, and we want to differentiate it. Again, very simple. You can, since we've learned implicit differentiation, let's stick with implicit differentiation. So the base here, we don't want that. So what we can do is that we can just take natural log both sides. And since sine x is just a power, we can make it as a coefficient of ln. So yeah, we can just move it down, okay? And now this is in a function in terms of y, this is a function in terms of x, so we differentiate both sides by x because we are looking for dy over dx. So differentiate sine x, we have cosine x. Ln a is just a constant, so we leave it. Again, we use chain rule, the variables are not synchronized, and we will have this. I'll do it a bit quickly. So dy over dx equals to, we move y, and y is a to sine x, right? So a to sine x times ln a times cosine x. Simple, right? Question 2. So when we have something like this is also very simple. So first, all right, for this one, let's not try to use, should we use implicit? Okay, I'll try to use implicit. So first, if we want to find dy over dx, we use product rule first. So because it's a product of two different functions. So we differentiate e to x, it's just e to x, and we leave log base 2x. And we leave e to x, and we differentiate log base 2x. But we don't know what to do, right? Then what we can do is that we can use chain rule. But what chain rule? Substitute the entire thing. And then apply implicit formula, implicit differentiation. So how did we do this? So you have to find du over dx because log base 2x du, right? Du over dx, we have to find this. So what we can do is that since we can't, assuming that we can't differentiate this directly, reform this a bit, and then differentiate both sides by x. And we already know the result of base a to x, right? So if we have a to x, if we differentiate it, we have ln a times a to x. So that one will give us ln 2 times 2 to u equals to 1. And there's du over dx. So du over dx would yield 1 would be 1 over root 2 times 1 over 2 to u, but u is that, so we have x. So just simply put that in. So e to x times log base 2x plus e to x times 1 over ln 2 times 1 over x. So that's how we can differentiate these two functions. Okay, So yeah, these are the, I say simple, I'll say these are simple examples, because what I mean by simple is that they're considered simpler than the examples that we are going to do right now. So finding a tangent and normal line. So for example, so we all know how to find the tangent or normal, right? So since we're looking for a line of an equation, equation of a line, so we just need to find the gradient and the point, right? So that's it, same thing. So let's say a function is like x cubed plus 2y to x, y squared equals to 3. And we want to find the tangent at this point. So first, check whether this point lies here or not, because remember, there are some special case where the point is not on the line. Oh wait, do I have this? Okay, never mind, sorry, I don't have it. But yeah, in the previous video I've covered it, right? So the case where the point is not on the line, then we have to make the point, right, of the tangent and do it. But so for this one, it lies on this equation. So let's try what we know. So again, you have to find this equation. So C point is already given, and we just need to find this gradient. And in order to find the gradient, what do we need? We need the differentiate function of y in terms of x, right? We need dy over dx, because why? That gives us the equation of the gradient. So let's look for dy over dx using this. So first, differentiate both sides by dx, by x. So same thing, 1 by 1, x cubed, then 3x squared. All right, so this is the constant, so we just leave it. And it's a product of two functions. So we differentiate y first by x, but we don't know what y is, so we leave it as a differential, like this derivative. And we leave it. Plus, again, we have a constant out, and we leave the first function, and we differentiate the second function, which is just the same, a to x. And this is y squared. So if we differentiate y squared by x, we don't know, so we just leave it like that. And differentiating constant 3 is just 0. So let's perform a bit more calculation. So alright, so again, y squared is a function in terms of y, and we have to differentiate it by in terms of x. So what do? We use chain rule. So dy squared times dx over dx, and then we multiply by 1, switch the order, then we have this. And differentiating that, we'll have 2y, and then leave dy over dx. So that's why we have this. And now we have the terms involving dy over dx, and that's what we have to find. So factorize it by dy over dx. And move the unnecessary parts to the right-hand side. So these. And then we divide this down there. So we have the equation of dy over dx like this. And now this is the equation of the gradient, and we want to know the gradient at this point. So in the previous questions, all the functions were explicit, right? So they were just in terms of x. That's why we just needed the x coordinate. But now, as you can see, the equation of dy over dx involves both y and x. That means you need the full coordinate, okay? So dy over dx at point 0, 1. So x is 0, so that's 0. y is 1, so that's 2, and that's 1, so negative 2. So again, that's 2, and that's 2, so it's negative half. That's the gradient, and we're done. So we know the gradient, right? And we just need to find c, plug this coordinate. So 1 equals to c. Therefore, the equation of tangent looks like this. Okay, good. There are some special cases where you'll have two different values for dy over dx. Oh, not like this, but so for example, let's say find the equation of a tangent at x equals to, for example, 2. Then in some cases there could be multiple values of y, because you can see that, for example, y squared, right? Then even if you substitute all x, replace all x by 2, so by substituting, yeah, you can have a quadratic formula, and you have two different values of y. That means you have two different points. Then two different points, that means you may have two different gradients, and two different gradients means you have two different lines. And that makes perfect sense, because most of these implicit functions, so I mean not most, some of the implicit functions will look like familiar geometry, like ellipse or a hyperbola or circles, whatever. And x at 2, that means we have two different points, and we can have multiple tangents, so that's absolutely fine. Okay, so just don't panic about that. It's very natural. Now, last example that I'm going to try is a bit difficult. So it's the example about rate of change. So yeah, as you can see here, it's a bit messy, so I'll just write it down again. So we have a ladder, 10-meter ladder, leaned against a wall. So the bottom of this ladder is being pulled away from the wall. At a rate being pulled away with 5 cm per second. So every second it's being pulled by 5 cm. And we want to find the change in vertical distance of the ladder when it is 6 meters away from the wall. Alright, so it's messy again, but yeah, so at least you get the question, I hope. So we have a wall, and we have a ground, and a ladder is leaned against the wall like this, and the ladder is 10 meters, right? And it's saying that the ladder is being pulled away with at this rate. So you can see that if the ladder is being pulled away, then it will go vertically lower and lower and lower, right? So we're going to look for this change in this value. So let's say this horizontal distance as x and the vertical distance as y, because we need these two. Why? So first, 5 cm per second, what is it? This is the change in the horizontal distance. So dx over dt equals to 5 cm per cube. All right? And we are looking for dy over dt, right? So remember all the rate of change question, write the conditions down first in derivative. And we want to find dy over dt at what? At x equals to 6 meters, right? 6 meters away from the wall, so 6 meters away. Then again, and like in any other rate of change question, let's derive the equation first. So we sorry. So we need the equation involving y and x together. So very simple, right? Pythagoras. So this diagram is very simple. So 100 equals to y squared plus x squared. That means y equals to root 100 minus x squared. And we reject negative because y cannot be negative. Y is a vertical distance. How can that be negative, right? So we just consider the positive part. And now we look for dy over dt. So dy over dt, then we can apply chain rule, but again this is implicit. It's a kind of an implicit function. Okay, actually you can do this, but as you can see you have to apply chain rule a lot. So I mean it's absolutely fine to do it. So you'll have this, but it's a bit difficult if we do step by step. So what we can do is why don't we just use this? So using implicit differentiation. So we differentiate both sides by t. So this is the use of implicit differentiation. Sometimes if you're more familiar with implicit differentiation, it can be much simple to differentiate a function even if it's explicit. So something like this. So that's 0. Alright, so let's look for this. We differentiated term by term, right? And the variables are not synchronized, so we have dy over dt times 2y using chain rule. And since we've done a lot of chain rules, so I'll skip. Can I skip? Maybe not. Maybe not. Okay. So we use chain rule. We have dy over dy squared over dy times dy over dt. So that's 2y times dy over dt. So we have this, and exactly the same thing. So x just being y. So dx over dt times dx. All right. So we want to find dy over dt. So dy over dt equals to negative 2x over negative 2x times dx over dt, and divide by 2y. So 2 cancels. So negative x over y times dx over dt. Then in order to find dy over dx, dy over dt, dy over dt, we need x, y, and dx over dt. But we know dx over dt, right? It's 5. And we know x, 6. But what about y? What's y? Oh, actually, it's in meters. So this should be 0.05 meter per second. 0.05. Right. So what's y? Okay, the hypotenuse is 10. The base is 6. Then this should be 8 using Pythagoras. So that's 8. So that's meters per second. So of course this negative sign makes perfect sense because it's decreasing, right? So decreasing rate must be negative. Okay, so that's it for this problem. Okay, so that's it for IBHL calculus, I believe. Alright, so we have covered all this, all that, and we have done concavity, point of inflection, optimization, everything. Yeah, and yeah, we've also done basic kinematics, not integration, but yeah, kinematics involving differentiation. So next lesson I'll go over integration. So you're done with IB differentiation. All right, so see you in next lesson. Bye.